when you have sloping ground, say that is the bedrock, and this, let's say, is the saturated loose sand, and this is clay. So this problem was huge in Japan, where superficial crust they had clay and some saturated sand. Now this slope angle can be very shallow. This angle, say if I call it beta, could be anywhere from 3 degrees to 10 degrees. So 3 degrees slope you normally cannot detect by eye. If you walk onto the ground and if the ground is sloping at 3 degrees, we'll say human eye is not very good at detecting slopes, especially shallow slopes like that. So everybody thought it was all great, and then when the earthquake happened, obviously this stuff liquefied and moves along this direction, but as it does, the clay also goes for a ride with it. Now the problem is, if I then imagine I got a pile going through here, I'll get some amount of lateral pressure on this. That's the first problem. How do we estimate that? And more important than that is this clay. Now suppose this clay has, say, undrained shear strength SU of 50 kPa. Yeah? So I'm putting, the clay wants to go down the slope, but I'm putting a pile in its path, and the clay itself is quite strong. So the amount of lateral load that applies can be very big, and this was causing a lot of extra load onto the pile, and in fact causing the piles to either bend or fail because of the crust load. So liquefiable soil applying load is one thing, but if you have non-liquefiable crust on the top, that was even bigger problem for pile foundations. Does that make sense? So kinds of earthquake related problems. If there was, unless you make meters per second, if it's fine, you put a plastic sheet on the top, and you can use, this is what we mean by bending. You can see the other way, come lay distance to 0.75. This is empirical, so it's just trying to fit some field data and get this equation, t to the power of half and theta to the power of 0.3. Theta is the slope angle in degrees, and t, I believe, is the thickness of the clay layer, of the liquefiable layer. Okay, and all I did here is to plot slope angle versus lateral spreading for different thicknesses. So clearly the thicker, another way to predict the amount of lateral spread, these are Americans, okay, Bartlett and Youth. Youth is a fairly famous researcher, and I think he has a company now, anyhow. So they had collected 467 field cases of lateral spreads and came up with this equation. Whenever I see equations like this, my antenna go up and say, if you are putting so many logs in any equation, that basically means we don't understand the mechanics. If you plot on log axis, almost anything will become linear. You can plot earthquake strength versus stock market. As long as you make both axes log, you will get some correlation. That doesn't mean stock market exclusively varies with earthquake strength, does it? It's just a correlation. When you do statistics like this, I get a bit upset. That is because they're not showing any understanding of what's going on. I'm not saying this is as random as stock market variations, but you can see they picked up some reasonable things like the earthquake magnitude, moment magnitude. R is the uh, horizontal distance to nearest fault. S is the slope. This is clearly important. S is important. M probably is important. Why did I say probably? English is like a bit funny language like that. When I say probably, that means it is may or may not be true. Why am I saying that? You heard me plans, it should depend on earthquake strength. Go on.
For example, you show that earthquake was far away but still.
Yes, that's one thing. The answer I'm looking for. Okay, so this fault distance also basically tells you what is the strength of the earthquake you can expect. If the fault distance to your actual site is very long, you expect the moment magnitude to be smaller. So they thought maybe we'll include that as well. And this is why they're not very clever. And then T15, this should be T sub 15, is the thickness of the saturated layer, liquefaction. So if I have 30, 40, 50% of fines content, then the liquefaction potential drops. The smaller the fines content, clean sands are the easiest to liquefy. And I think that was covered. Sub 15 is the average D50 grain size. I did one calculation, 100 or 500 millimeters. If this spread is going to be bigger than that, I will already mobilize evidence for that. Especially a historic, all these 467 case histories, you can predict ones, which is on the unsafe side. Okay. So this kind of plots are available, and again you can see these are done by American researchers. That's why these are all in horrible FPS units. What this is trying to do is to see the displacement, lateral displacement in inches plotted against the depth of the layer in inches, liquefiable layer in inches. And what it's trying to do, rightly or wrongly, is the slope is taken as 20 degrees. And what it is saying is when you shake it, what is the mode shape it will go to. So it can start somewhere like going upslope here to like this to downslope there. So cycle by cycle, I can accumulate movement towards the downslope. Okay, so if I have 10, 15 cycles, I can accumulate quite a lot of displacement cycle by cycle. And for the same data, I can also work out what is the shear stress on layers parallel to the slope. And these are plotted as shear stress in pounds per square inch, which is a favorite unit for the Americans. Pound is a force, obviously, but pound is also weight. So obviously what they mean here is LB force, pound force per square inch. We can sit down and convert all this into kPa quite easily. So 1 pound is 2.2 kilos, so it's about 22 newtons, and inch is 25.4 millimeters. Convert that into meters, and you can convert that into kPa with a factor. And again, you can see how the shear stress is more on when it's trying to go upslope, and it drops off. As the soil liquefies, obviously, the shear stress will become quite small, and that's why it's flowing. So this is quite right that at the end of the shaking, I got very little shear stress in the layers. Does that make sense? Yeah? Okay, anyhow, these are the plots one can get. But this is all to show that if I take an element here, soil element here, and track how it moves, it's going to oscillate and back and forth, and cycle by cycle, it will end up somewhere here. So it's not going to go like that. It will oscillate and it will go down. And in the video I've shown you yesterday, that was also what we observed, right? So that was on a 3-degree slope, I think I showed you. Right. Now let's do some proper mechanics. As I said, we are always focused in this course. It's you need to understand the mechanics of the problem to make predictions. In the absence of mechanics, you come up with empirical relationships. Some are good, some are bad, some are simple, some are a bit more complicated, but nonetheless, there's always an element of guesswork in that. It all depends on how good or bad your actual field data is. And even if AI takes over the world, for these kind of problems, it will struggle because the data we are giving it is quite bad. If data is bad, it can't come up somehow with the right mechanics. That we have to still do. And that's why I feel geotechnical, somebody was asking, is there future for geotechnical engineering in the era of AI? And I believe yes, because for good or bad, we actually don't understand soil all that well. If we don't understand, there's cat in hell's chance that AI can tell us what the soil is going to do. So first, humans should know what's going on, collect a lot of data, and then AI can help. But in the absence of that, there is very little chance that we will make progress with AI. So I wanted to kind of come back and teach you how to use this Newmarkian sliding block analysis. Newmark had the real honor. He was a professor of Berkeley, and the very first Rankine lecture he gave. Rankine lecture, have you heard about Rankine lecture? Hopefully, if you're in geotechnical engineering, you should have heard. Rankine lecture is about is the best honor anybody can get, you know. And the very first one he gave, and what he did in his Rankine lecture is came up with this very simple mechanical sliding block. Okay, and I'm going to explain what that is. So it's particularly relevant for the problem we are trying to do here. This new board. So all he did was, imagine I got a slope with some angle. Yeah? And you have a block. So that block has a mass m, right? Even first year engineering student should know this. We will have a normal reaction to this, and what else will be there? I will ask some other student. Go on. What else should be there? So this is normal. There should be one more force, right? So mg is that way. Yeah. And I should have some R that way, right? Because the block wants to slide down, I'll get frictional resistance to oppose it. And mg cos beta will be one, mg sin beta will be the other, and we can work out the equilibrium of that, right? That is a block on a slope problem. A-level students should do that, or intermediate students should do that. Now, what he said is, let's imagine I'm going to shake this whole thing with some acceleration. So I'm going to shake this whole slope. What will the block do? Sorry?
Will start to slide after some time.
Okay, let's imagine I'm only going to apply a sinusoidal pulse. So this is my acceleration with time. Okay, that's what I'm applying at every point. So that's the acceleration pulse I'm giving it. So what will the block do? Okay, good. That is one answer. If I shake this strong, so I'll have the block which wants to slide down, but it's being held by their resistance force. If my downward acceleration times mass, if that force is bigger than R, then it will slide, right? In that first positive cycle. But in the negative cycle, the block is being accelerated upslope. If my pulse is big, it can also slide upslope, right? So, what he basically said was, because these are all forces and I can divide the force by mass to get acceleration, what he said was, if I exceed a certain threshold acceleration, the block will slide, which is obvious to say. It's fairly basic mechanics. Going the upslope side, this is what is called threshold acceleration. Threshold for sliding. Wow. Yeah? When I want to slide upslope, this magnitude will be a bit bigger, because now I need to overcome the R in the other direction and still go up, right? So if it is, say, here, then the block will not go up slope. It will only go down slope. But if it is maybe here, then it will go up as well. Okay? Right. So this threshold yield acceleration is what he was proposing. So he's done this for earth dams and how these slopes fail. If you go back, put into Google Newmark's Rankin lecture, it's all online, and he's done it to show earth dams can fail because of these type of accelerations. The upslope and downslope of an earth dam can fail because of this. At that time, it was quite important for people in Berkeley, because they had 3 or 4 San Fernando Dam and lots of other dams all around Berkeley. They had the what is now called Los Angeles Dam, but upper and lower San Fernando dams had some damage during earthquakes, and he thought this is an important topic to address in a big lecture like Rankin lecture. So that's what he's done. So if I now have more cycles, what will happen? So during this period, it will, because I'm only looking at one cycle, in that period from here to here, the block will slide. Yeah? But if I have more cycles, for every cycle, as soon as I cross the threshold acceleration, I'll accrue some more displacement downslope. Yeah? If I had a little bit of upward movement, then the block can go a little bit up. So it can do that, little bit that, more, little bit that, more that. Or it can do that, stop, that, stop, that, stop. That's what this mechanical model can predict. Anything you're not sure about, especially back of the class. Is this easy enough to do? Yeah? Right. So that is the fundamental concept that Newmark has come up with. And once I can get this concept in my head, then I can actually do some calculations. So, if I integrate acceleration, what do I get? You get velocity. If I integrate velocity, what will I get? So, what we can do is, can I rub this out? You got this, right? So, I need a bit more space because I can only use this part, right? This part you can't see. Okay, we'll work around that. So that is my acceleration versus time. Yeah, let's, for sake of, let's say that's just 1 hertz pulse, and let's say that is about 0.4 g. Okay, and our threshold acceleration, let's set it at 0.3 g. And on the downslope, this will be also be 0.4 g. Let's say that this is 0.6 g. So this type, if this is the case, I'll only get movement downslope and nothing upslope. Agreed? Okay. So what I want is to first, so I'm only interested in the acceleration above the threshold. In other words, this part. Yeah. So I'm going to plot the leftover bits here. Yes? Then you want to say, I'm going to integrate that to get my velocity. So that whole area, you know how to get area underneath a curve, right? Yes? So this will come out to be, so each bit you take as a little area, add that, you get a pulse like that. Yes? And same will be here, same will be here. And now I can do displacement versus time. One of the things you will see is, although acceleration is 0 there, the velocity actually will take some time to come to 0. The fact that acceleration has come to 0 means the body is not being subjected to acceleration, but it still has some velocity, right? So the displacement will accrue until velocity comes to 0. It basically takes, it's like stopping distance for a car. The stopping distance you calculate not based on acceleration or the braking force, but based on velocity coming to 0. It's the same thing here. So a lot of people who do Newmark calculation actually don't understand this and make that mistake. Oh, my acceleration stops 0, therefore my body should stop. No, it will continue until velocity comes to 0. Right, so that, now I can do this, then I can actually plot these displacements. So if I were to look at how this will accrue with time, it look like that. This will be displacement versus time accumulated plot. Does it make sense? So it will accrue displacements whenever it crosses the threshold acceleration. Yeah? Okay. So the block will slide and continue to accrue downslope displacement until the velocity falls to 0, and the sliding block can only slide upslope if my threshold acceleration uh, is reached on this side as well. So you can, if for a very steep slopes like 10 degrees, 6 degree, 10 degree slopes, the acceleration needed to go upslope will be quite high. But for 1 degree, 2 degree, 3 degree slopes, it may not be that much. Then you can say, right, it's not going to be 0.6 g, it will be say 0.35 g. And then you'll get bits here as well. Okay? And you must remember that is going upslope. So these, although you may get integrated values may be positive, but you must have the sense to say, no, my actual displacement is the other way. Yeah? So you will get something like a decrease here, and then followed by down to 0, and then integrating that to displacement will give you something like that. Because I'm only plotting the whole, I'm always adding to the cumulative displacement. So you get something like 10, 15 millimeters. This is all at centrifuge scale, so you got to multiply that with n. But that demonstrates the principle of it. Right. There are more sophistications that can apply to Newmark. In fact, Bruce, Cutter, and myself were great fans of this. We're all Cambridge trained, so we are really into mechanics and estimating things based on mechanics. So he uses this. I recently used this to predict the, with a student, of course, flotation of a tunnel. Soil liquefies around the tunnel and it floats up. You can do FE stuff and so on. I think I showed you an example of that before. But you can actually predict the upward movement simply by using Newmark's same concept of threshold acceleration. And it works beautifully. Because the mechanics is easy, it should work. Anyhow, if you, for liquefaction problems, we don't have this kind of sliding block alone. What we have is, when you are having this lateral spreading, it's really the excess pore pressure that is killing the strength. Once I got excess pore pressure, my effective stress comes down, which means my threshold acceleration to cause sliding is decreasing, right? So instead of being something like 0.3 g, that one will drop to say 0.05 g. Then I get huge amounts of spread, because now I'm integrating much bigger area, all this area will be included, right? So the threshold acceleration is coming down because of the excess pore water pressure. And that is what reduces the strength of the material, or the sliding resistance capacity, if you like. Cutter and Balakrishnan, they had even bigger, grander ideas of trying to link this. Yesterday I mentioned that you can, the soil, when it fully liquefies, if you try to shear it, it will undergo dilation. And the dilation expresses itself as deliquefaction shock. We had done that yesterday, right? So they tried to put that back into Newmark sliding block, where this line is not like that, but it can do. So say the threshold, I'll redraw it. You understand this, right? I'll clear this off. So what we are effectively saying is, okay, I got my 2 cycles. Say liquefaction made my threshold 0.05 G. Let's say that's 0.4 G, like before. But when I get this deliquefaction shock, this thing stays like that and jumps up. Does that make sense? So you can say the deliquefaction shock will create a temporary increase in your threshold acceleration, which means I can still handle this. It's not complicated. All I have to do is to say, I'm going to integrate the area between this bit. Yeah? Is that right? No, sorry. This bit. That's what we're looking at. So you can do the sine wave cut, integrate that, and subtract from this trapezoid. So it will reduce the amount of lateral spread. And that is quite right, because what the suction is doing is stopping the slope from moving, right? So it moves, stops, moves, stops, right? So if I have suddenly the pore pressure is going into negative and stopping the stiffening my soil, I expect smaller lateral spread to happen. So what started as a simple block on the slope has kind of, we are now putting higher and higher ragas and swaras and making it more complicated. However, the mechanics is still very simple. We can include some of these other features into this same idea of downslope movement. And this also explains why in the centrifuge tests and experiments we do, why we see the slope suddenly stops and then moves and stops and moves as well. And it's all linked to pore water pressure. In whole of soil mechanics, as I said yesterday, there are only one big thing you need to understand. The soil behavior is linked not only to the stress state it is in, but it is also dependent on its tendency to have volume changes. It's unique in that sense, unlike steel, concrete, any other carbon reinforced fiber, every other material, man-made material, granular materials like sands and even powders in chemical engineering, these have the unfortunate habit of trying to change their volume. And that's what makes it so exciting, because it's not easy. You can't map everything just based on stress. You have to worry about the third dimension, which is the change in void ratio, or in Cambridge we call it specific volume. It's the same thing. Okay, so Q, P dashed, and V is what the dimension, the 3D space you got to work in, and this is another classic example of that. Okay, last thing before we stop for tea. Oh, sorry. Some experimental evidence. This is, I think, all the way going back to my second PhD student. We could, if you log the data quick enough, you can see these are very small times, right? This is in tens of milliseconds. You can see, so this is the earthquake we applied, more or less sinusoidal, and these are the pore pressures along the height, so deepest to shallowest, and we kind of zoomed them quite big, right? But what you can see is, you can look at this deliquefaction shock wave propagating. So this is not some myth that we created. You can actually see that in almost every centrifuge test we do. And that also tells you how, because it's a P wave, that is, it's a pressure wave, you can work out lots of other things. Like if I know P wave velocity, I can tell you degree of saturation and all kinds of other things. The Skempton's B parameter and other soil mechanics related stuff also falls out of this. But the biggest thing here is what Cutter and Balakrishnan said are the deliquefaction shocks. We can observe directly from the data. And this is Haskell's data I was showing yesterday, Jenny Haskell. Only one disappointment with this work is this New Zealand girl came on the Rutherford scholarship, worked very hard for 3.5 years, produced most wonderful experiments, wrote one geotechnic paper and some other conference papers, and then she got a lectureship back in Christchurch. She went there. 2 years later, she decided soil mechanics is not for her and went to Australia to study medicine. I said, what? I still don't know how far she got into her medical course. My daughter is still studying, and my daughter is a lot older than this girl. There's no end, right? After doing so much good work, why want to change? Anyhow, again, this is the evidence of propagation of the deliquefaction shocks in there. Weird people, New Zealanders. And you can look at the, I showed you this data yesterday as well. So it's basically, I'm showing now in the context of the suction cycles you're getting. Right. This is the bit I really want you to do. Okay. So either you take a photograph or you probably will get this slide through the website. What I want is take a slope of 10 degrees. Okay. And let's imagine it is simply loose saturated sand, fully submerged. Okay. For the sand, let's say the peak friction angle is 35 degrees. So we are going to approximate the slope as a rigid block, and I would like you, the amplitude of the sine wave should be 0.6 G and the frequency of 1 Hertz. I'd like you to estimate the lateral spread, and you take the yield acceleration of about 0.2 G downslope and 0.4 G upslope. Okay? If nothing else, draw the sine wave, shade the area, count the squares, and that is also integration, right? So you can do it in any way, any number of ways. What I want for tomorrow is an answer. And if you had to make any assumptions, just explain. This is the critical point. Yeah. Instead of having 1 Hertz shake, if the frequency has gone up to 3 Hertz, yeah, redo the calculations for 3 Hertz. Again, still considering only one cycle. First one, you are taking one cycle. Second one also, you're taking one cycle. It's just the frequency is different. Okay? And I want you to tell me what you observed. What is the effect of frequency on the lateral spread? Just out of the cold, what do you think the effect of frequency will be?
Maybe rate of lateral spread faster.
Maybe, but we are worried about magnitude, right?
But the rate is also matter.
Okay, do the calculation.